Check it out now, y'all.
nanoHUB-U, online instruction.
Okay, we're ready to start lecture 1 and to dive in and derive the thermoelectric transport coefficients. So we're going to be using a non-traditional way of doing this derivation. It's the bottom-up approach that Professor Dada discussed in week 1. I'm going to refer to it as the Landauer-Boltzmann approach. This approach is commonly termed the Landauer approach. It can be derived from a quantum kinetic equation. That gives people the idea that it's fundamentally quantum mechanical and applies to small structures. But it can also be derived from a Boltzmann transport equation and can apply not only to small structures but to large structures in a semi-classical perspective. That's the viewpoint that we're going to take. We're going to be using the Landauer approach but thinking of using it in a semi-classical way. So there are 3 topics for this lecture. The one is to derive those coupled current equations. We'll just review them very quickly. Then we'll derive them using the Landauer-Boltzmann approach. And then we'll look at more carefully at deriving each of the transport coefficients. So this is the experiment that we're doing again. We force a current through a resistor. We impose a temperature gradient. We measure the voltage across the 2 ends of the resistor, and we measure the heat current that flows, and we want to be able to relate all of the quantities that we force to the quantities that we measure. And the key to doing that are a set of thermoelectric equations, and we're going to be looking at deriving the equations for the electric field or voltage that we measure across the resistor, for the electronic part of the heat flow, and for the lattice part of the heat flow. And we'll try to develop expressions for all of these transport coefficients. Now, if you look in textbooks, you see many different ways of writing these transport coefficients. Most of them look a little bit complicated. So here's one way of writing them that you can find in Gang Chen's recent book. Here's another way of writing them that you can find in this famous paper by Mahan and Sofo. We're going to be looking at this particular expression, but they're all equivalent in the end. And we're going to be trying to develop an understanding for where these equations come from, an understanding for what this transport distribution is, and we're going to be doing that using this Landauer-Boltzmann expression for the current. So we have this, our conceptual picture then is, we have this small nano device, which eventually we're going to make very long and think of it as a large bulk device. We have 2 contacts to the device. Each of the 2 contacts is a large region with lots of inelastic scattering that is maintained in thermodynamic equilibrium at all times. So each one has a well-defined Fermi level, but the Fermi levels may be different if the contacts have different temperatures or different voltages. We're going to be using the Landauer-Boltzmann expression for the current. As Professor Dada discussed, fundamentally what makes current flow is a difference in the Fermi functions. And there is this conductance function, which then relates the current to the difference in the Fermi functions at each energy level, and we integrate over all of the energy levels. And we're going to be rewriting this equation in a mathematically equivalent way that is more convenient for my analysis. So we have a set of fundamental constants called the quantum of conductance, a quantity called the transmission, a quantity called the number of modes or channels for current to flow, and then the difference in Fermi functions, F1 minus F2. Okay, so let's talk about each of those quantities: transmission, number of channels, and the Fermi function difference. So in transmission, the transmission in our semi-classical point of view is just a number between 0 and 1. So we can think about having a slab of material of length L, mean free path lambda, which is the average distance between scattering events. It's a stochastic variable, but it's the average distance that an electron travels. So if we inject a flux of electrons on the left side of this slab, they scatter and undergo a random walk. Some fraction of them exit the right side, and that fraction is just what we call the transmission. It's a number between 0 and 1. Assuming that there's no recombination generation, then electrons don't disappear or appear magically. Particles are conserved. Those that don't leave from the right return and exit from the left. And we would call that a reflection coefficient, just 1 minus the transmission coefficient. So that's what we mean by transmission. Now, it turns out that if you look in either Professor Dada's book or mine, you can find a simple derivation that relates that transmission coefficient to the length of the slab and to the average distance between scattering events. And the expression is very simple. It's mean free path over mean free path plus the length of the resistor. And you can see that that's always going to give you a number between 0 and 1. Okay. Now, if we look at the limit where the length is much longer than a mean free path, the transmission gets very small. We would say that we're in the diffusive limit then, and the transmission is about mean free path divided by length. For the first few lectures, we're going to be in this traditional bulk thermoelectric diffusive limit. Later on, we'll talk about the ballistic limit where T gets close to or exactly equal to 1. Okay, so that's one of the important parameters, the transmission. The second parameter was the number of modes at energy E, M, or the number of channels. Physically, you can just think about that as lanes on a highway. So here we have my university, Purdue, which is about 2 hours away from Chicago. We have a 4-lane highway, 2 lanes to go to Chicago, 2 lanes to come back from Chicago. They carry a current of vehicles, cars and trucks and whatever, motorcycles. We would say that we have 2 channels for current flow, 2 to Chicago, 2 from Chicago back to Purdue University and Lafayette. So the channels are just lanes for current to flow in. Okay. Now, we can think of it another way. We can show mathematically that the number of channels is proportional to the density of states. The more states we have, the more channels, but we have to have a velocity. The electrons have to move in those states. So the number of channels is proportional to the average velocity in the direction that the current is flowing times the number of states at that energy. Okay. Now, if we have parabolic energy bands, then things are relatively easy. The velocity, 1/2 mv squared, is just the kinetic energy, E minus bottom of the conduction band. So we can simply relate the velocity to the energy. Now I have to worry about the average velocity in the direction of current flow, in the direction of the resistor, the long part of the resistor. In 1D, there is only one direction. So the velocity, the average velocity in the direction of current flow is just the velocity. In 2D, I have to average over the angle in the XY plane. So the average velocity is a little less than the magnitude of the velocity. There's a factor of 2 over pi, because some of them are pointed in a direction that's more close to normal to the current flow. In 3D, the factor, when you do that angle averaging, is 1/2. Okay, so that's the average velocity in the direction of current flow. Then we just multiply by the density of states. So the density of states is something that we are familiar with from basic semiconductor physics. In 1D, it goes as 1 over the square root of energy for parabolic energy bands. In 2D, it is independent of energy as long as we're above the bottom of the band. In 3D, it goes as the square root of the energy. So we draw these pictures that are very familiar if you've had a semiconductor book. It's very important to understand how the density of states varies with energy. In 1D, the density of states goes to infinity at the bottom of the band. In 2D, it's constant above the bottom of the band. In 3D, it just increases slowly as the square root of energy. And in more complex band structures, we have more complex shapes. Now, the number of channels is velocity times density of states. And velocity goes as the square root of energy. So if we plot the number of channels versus energy, we simply get a constant for 1D, because we have 1 over square root of energy times square root of energy. In 2D, the number of channels increases as the square root of energy. And in 3D, the number of channels increases linearly with energy as we go above the bottom of the conduction band. Same thing would happen for the valence band. It would increase linearly as we go below the bottom, below the top of the valence band. Okay. So that's our current expression. Some fundamental constants. If we make the structure very, very small, we'll see that current is quantized in these units of 2Q over H. The transmission is just a number between 0 and 1, which tells us the probability that an electron that comes in the left contact goes out the right contact. M is just the number of channels there are to carry the current at that energy. F1 minus F2 is the difference in the Fermi functions at that energy between the two contacts. No current flows unless there is a difference. And then we do an integral over all of the energy channels to get the total current. So the key things are understanding transmission, the number of channels, and the difference in Fermi levels. From these concepts, we can derive the thermoelectric transport coefficients. Okay, so we need a difference in Fermi level in order to make current flow. How do we get that? Well, there are a couple of ways. The easiest way is maybe to apply a voltage difference across the two ends of the resistor. So if I have my first contact that has a Fermi level of EF1 for the first contact, in equilibrium, the Fermi level of the second contact will also be EF1. But we learn in basic semiconductor physics that if you apply a positive voltage, you pull the electrochemical potential or Fermi level down. So a positive voltage on contact 2 will lower the Fermi energy. Now I'm going to have a difference in Fermi functions between the two contacts, and current is going to flow. Okay, now the other way to produce a difference between the two contacts is to change the temperature of the two contacts. If these two contacts are at different temperatures, T1 and T2, their Fermi functions will be different even if the voltage is the same. So the two ways that I can make current flow are to apply a voltage or to apply a temperature difference between the two contacts. In both cases, I'll get a difference between F1 and F2 and current flows. Okay. Well, let's look at the first case where we have a constant temperature and see what happens. So here's my Fermi function. For energies way below the Fermi level, the probability that a state is occupied is close to 1. For energies way above the Fermi level, it's close to 0. At the Fermi level, the probability is 1/2, and the transition from 1 to 0 occurs a few kT about the Fermi level. If contact 2 has a lower Fermi energy, because we've applied a positive voltage, we'll just shift everything to the right. And now you can see that there is an energy region over which F1 minus F2 is positive and current will flow. So an applied voltage at the same temperature between the two contacts leads to current flow. Okay. This region over which current flows is something that I'll call the Fermi window. It is the range of energies over which F1 is different than F2. That's where all the action occurs. Okay. Now, as Professor Dada discussed, if we apply a small voltage, and in the thermoelectric problems that we'll discuss for the most part in this week, we'll simply be talking about small applied voltages, then F1 minus F2 can be expanded in a Taylor series. And you would guess that this difference is going to be proportional to the small voltage that you apply. And indeed, that's the case. We can show that F1 minus F2 is proportional to minus the derivative of the Fermi function times Q times the applied voltage. So we can make that approximation when we apply a small voltage, and that's what we're mostly going to be concerned about in week 2. Okay, that applied voltage there is simply shifting the Fermi level of contact 2 by amount delta F, and that's what's leading to the current flow. Now, there is a different way that we could lead to current flow. We could have the same voltage between the two contacts, so we have the same Fermi level. Fermi level in contact 1 is just what it was before. Now, if contact 2 has a hotter temperature, then the transition between 1 and 0 is spread out in energy, and now we have a difference between the Fermi functions between the two contacts. It's interesting to note that in this case, below the Fermi level, the difference F1 minus F2 is positive. Above the Fermi level, the difference F1 minus F2 is negative. That's what leads to a change in sign. For example, the thermoelectric coefficient is negative for N-type materials, positive for P-type materials, because you're dealing with states that are either above or below the Fermi energy. Okay, so F1 minus F2 flows, but it depends on whether the states that we're concerned with are above or below the Fermi level. That will determine the sign of the current flow. Now, we can do the same thing that we did with voltage. When the voltage was small, we used a Taylor series expansion. When the temperature difference is small, we can use a Taylor series expansion. Professor Dada discussed this briefly too. You can get a similar kind of Taylor series expansion. It's a little more involved, but as long as the temperature difference is small, it will describe F1 minus F2 accurately. So both of those two cases, we consider near equilibrium thermoelectric transport, and that's what we'll be concerned with. Okay, so a recap. We understand transmissions, we understand modes, at least we understand enough to proceed, and I'll refer you to the references or to our lecture notes for those of you that want to understand those concepts in more detail. We understand what can produce differences between F1 and F2, so now we're ready to compute the currents and derive the thermoelectric transport coefficients. Okay, so let's take this step by step. Step 1. Let's compute the current, assuming that the temperature is constant. So we begin with our fundamental Landauer-Boltzmann expression. We expand F1 minus F2, assuming a small difference in voltage. We assume that we're in the diffusive limit. The sample is many mean free paths long, and we simply plug into this expression. We'll get a complicated looking expression. The important point is that the current will be proportional to the voltage as long as the voltage is small. So we can write the current as conductance G times voltage. And we now have an expression for the conductance in terms of mean free path, number of channels, and the Fermi window where F1 minus F2 is different. So relatively easily, we can get an expression for current and conductance. The conductance is given by this G prime, which we would call the differential conductance, and it is simply related to fundamental constants, mean free path, number of channels, and the Fermi window. Okay, so here's where we're at. You know, traditionally, if we have a large material, we like to think about conductivity instead of conductance. The conductance is conductivity times the area of the resistor divided by the length of the resistor. The fatter it is, the more the conductance, the longer it is, the less the conductance. So we can use that to re-express this term G in terms of conductivity, and now we get to one of the 4 transport coefficients that we're after. The electrical conductivity is 2q squared over h times an integral involving parameters that have clear physical interpretations. So we will write the electrical conductivity as the integral over the differential conductivity over all of the energy channels. The differential conductivity will play a central role in our expressions. It's 2q squared over h, mean free path, times the number of channels per unit area in the cross-section, multiplied by this Fermi window. Okay. So let's look a little more carefully. We know what the mean free path is. That has a very clear region, physical interpretation. We know what the number of channels is now. We know the physical interpretation of that. Let's look at this Fermi window. That's what came from the Taylor series expansion, F1 minus F2. And it's minus the derivative of the Fermi function with respect to energy. So you can see that the only place the Fermi function has a derivative is in this region a few kT about the Fermi energy. The derivative is negative. We have a negative sign here. So the Fermi window is this positive function sharply peaked near the Fermi energy having a width of a few kT. This is where all the action happens. This is where F1 minus F2 is different. We only get a conductivity in the energy range about the Fermi energy where the Fermi window is non-zero. Okay, so that's what we term the Fermi window. In a metal, the Fermi level is way above the bottom of the conduction band, and all of the action happens right around the Fermi energy in the middle of that band. In a semiconductor, in a non-degenerate semiconductor, the Fermi level is well below the bottom of the conduction band, and all of the current flow is due to a very small tail of the Fermi window that overlaps with the conduction band itself. Okay. Okay, so we've done step 1. We've done the resistivity, which is 1 over the conductivity. Let's do the heat current. So if I look at the heat current, I'll look at how much heat current does that current flow produce. And here there's a very simple physical way to look at this, and I'll recap quickly what Professor Dada discussed. I have my two contacts. In the metal, the Fermi window is at the Fermi energy. The current is all flowing at the Fermi energy in contact 1. In the semiconductor, the current can only flow where there are channels, and there are channels in the conduction band. So we have to absorb heat in order for the electrons to gain the energy, go up from the metal, find a channel at some energy E in the conduction band, flow across the device in the number of channels that are there, and then deposit themselves in contact 2. So, in order for the first step to happen, we have to absorb thermal energy from the environment at contact 1. This we call Peltier cooling, and is the principle for a Peltier cooler. The second part, we dump that energy into the second contact. That's Peltier heating. So we have these two processes going on. If we have some resistance in between, we have some I²R joule heating going on in between too. But let's not worry about that for the time being. So we have some current density, some heat current. The electrons are carrying the heat that they absorbed across the device and then depositing them in contact 2. So let's see if we can analyze that. That current, well, we know what the flux of electrons is flowing at that energy. It's the electrical current divided by the charge on an electron. That gives us the flux of electrons flowing from contact 1 to contact 2. The amount of heat each of those electrons absorbed from contact 1 to hop up to that energy channel is energy minus the Fermi energy, where they started from in the metal. So this is the heat flow at energy E. Okay, now all I need to do is to rewrite the electrical flow in terms of the electrical conductivity. Then I can do an integral over all of the energy channels, and we very simply get to an expression like this. If I divide by the total current, multiply by the total current, you can see that I have heat flux is proportional to electrical flux or electrical current. And that constant of proportionality we call the Peltier coefficient. We have an expression for it here. And if you look at that expression, it looks a little bit complicated mathematically, but what it really is it's the energy with respect to the Fermi energy in the metal contact, weighted by the ease at which current flows at that energy. That's what the differential conductivity tells us. And then normalized by the entire conductivity. So what we're doing here is we're computing an average energy at which the current is flowing. And the Peltier coefficient has a negative sign out front because the states are above the Fermi energy, and F1 minus F2 is negative. And then it's related to the average energy at which heat flows or current flows minus with respect to the Fermi energy. So we have a simple expression for the Peltier coefficient. Okay. Well, now we've got a third coefficient. We haven't talked about the Seebeck coefficient. But this we can handle very easily in this lecture because Professor Dada mentioned that there is a fundamental connection between the Seebeck coefficient and the Peltier coefficient, the two coefficients that couple these two separate equations. And that fundamental connection is Peltier coefficient is temperature times Seebeck coefficient. This is known as the Kelvin relation. Since we've derived the Peltier coefficient, we have the Seebeck coefficient. So we have 3 of the 4 thermoelectric transport coefficients. The fourth one is the electronic thermal conductivity. This one takes just a little more work. I'll just go through it quickly, and you might want to go through it again on your own. What we seek is the heat current under open circuit conditions. That is, if I would open circuit the problem, make the electrical current 0, then the heat flow would be entirely determined by the temperature gradient and the quantity that we're after, the electronic thermal conductivity under open circuit conditions. Now, it turns out that it's easier to derive another electronic thermal conductivity. And that is, if we begin with this expression, it's going to be easier to do an electronic heat current under short circuit conditions, not open circuit conditions. And then we can fix it up later. So let's start here. We can take our expression for electrical current, and now we're going to be interested in heat flowing, not charge flowing. So we should replace the charge on an electron Q with the amount of heat that each electron absorbs as it hops from the Fermi level in the metal up to a channel in the semiconductor. We have to put that inside the integral because it depends on energy. Then we can use our same Taylor series expansion for F1 minus F2. That gives us a second E minus EF. And when we put those two together, we're going to find that the heat current is proportional to the temperature difference. All of this complicated business inside the square brackets is the electronic heat conductance under short circuit conditions, because when we write this equation here, we've assumed that voltage is 0. And when we do that, we get a simple relation for the electronic heat conductance under short circuit conditions. I can convert that to an electronic thermal conductivity under short circuit conditions, and we get an expression that looks like this. The mathematics looks a little complicated, but was all step by step and relatively clear physically. So we have a simple expression for the thermal conductivity. We'll recognize many of these parameters. These are the same parameters that appeared in the differential conductivity for the electronic conductivity. So we can lump those together in this differential conductivity sigma prime that we've seen before, and we have our final expression. We now have the thermal conductivity that we would measure if we short circuit electrically this resistor. But that's not what we're after. You know, if we look in these equations, what we're really after is this electrical conductivity. This is the electrical conductivity, or the thermal conductivity, that we measure when we open circuit the structure, not short circuit it. What we've measured is the parameter in this equation. This is gives us the electronic heat that current density that flows when we short circuit the structure and make the electric field 0. So we've got a thermal conductivity, we just don't have the thermal conductivity that we want. Not in this form of the equations that we most commonly use. So there's an easy way to get that. If I look at the electric field, and if I short circuit it, I can find out what current flows under short circuit conditions, and we find the current is proportional to the temperature gradient. Then if I look at the electronic heat current, my expression for it is this. If I evaluate this current under short circuit conditions, I'll use the short circuit current, and now you can see that everything is in terms of temperature gradient. And if I lump everything together, I'll find that the heat current that flows under short circuit conditions is pi, Peltier coefficient, Seebeck coefficient, electrical conductivity, plus the thermal conductivity that I'm after. And by equating these two expressions, we find that there's a simple expression between the thermal conductivity that we want in the form of the equations that we're writing and the thermoelectric conductivity that it is easiest to compute. It's just given by that relation. Okay, so finally, these are the equations that we've derived. These are the equations that we started with. The first important quantity is this differential conductance. This tells us how much current flows at each energy in the sample, simply related to some fundamental constants, mean free path, number of channels, and by the width of the Fermi window. To get the total conductance, we integrate the contributions over all energy channels. To get the Seebeck coefficient, it's simply related to the average energy at which current flows, so that's depending on the conductivity of each of those channels. Peltier coefficient we get from the Kelvin relation, which relates the two. And we've seen that we can derive the short circuit electronic thermal conductivity relatively directly from our bottom-up approach, and then we can translate it into the open circuit electronic thermal conductivity that we need when we write the equations in this form. Okay. Now, just a couple of more things to wrap up, and then we'll be done. I've sort of been thinking about the Fermi level somewhere above the middle of the band gap, and we've been thinking about electrons flowing in the conduction band, and we have some distribution of channels which increases linearly with energy if we have a parabolic band. Well, what about the valence band? And what about if the Fermi level is closer to the valence band, to the conduction band? Nothing really changes. we simply have a total number of channels that includes both the valence band and the conduction band and none in the middle of the band gap. And when we use our expressions, we just have to integrate from well below the top of the valence band to well above the bottom of the conduction band, and we'll get all of the contributions at the same time. So really, no changes are needed. We don't have to modify these expressions for holes. Our expressions describe electrons flowing, whether they're flowing in the conduction band or the valence band. We just need to be sure that we include the channels. Whichever channels are occupied and in the Fermi window, we need to include those. And it's a nice little exercise to show that your total conductance will be the conductance of the conduction band plus the conductance of the valence band, the conductivity. The total Seebeck coefficient will be negative for the contribution from the conduction band, positive for the contribution from the valence band, and we'll have a weighted sum depending on how much conduction there is between the two. So that's a little exercise that I encourage you to have a look at. Okay, so we've moved quickly this lecture, but some of this ground has already been covered by Professor Dada, and I wanted to show you how you translate those concepts into the actual expressions that we will use. So here are the expressions that we have derived. They look a little bit intimidating, but if you go through it step by step, and I encourage you now to look through the lecture notes and go through this again and make sure you understand each of these steps, you can see that it's relatively easy to derive these expressions that tell us no matter what the band structure is, as long as we know how the channels are distributed in energy and what the mean free path for scattering is, we're able to compute all of these thermoelectric transport coefficients. It'll be near the end of the week that we discuss phonons, but similar ideas will apply for phonons. Okay, so we've covered a lot of ground. That's it for Lecture 1. And in Lecture 2, we'll continue the discussion, but we'll be spending a little more time in trying to get comfortable in understanding these transport coefficients a little better. Thank you.